recording the session now? Yes, I hope I am. Okay, yeah, it should be. Anyways, yes, we can continue. You guys can still hear me, right? Just let me know when if something goes wrong. Anyways, again, I'd appreciate if more of you could show your face on camera. I appreciate those of you who do. I see you. I love you guys. Keen, Junyoung, Abhishek, Niang, Long Hao, Mrinal, Jack, Elvin, Hans. Do I just call you Hans? I don't know. Do I? Yes. Okay. So Hans, yes, thank you very much for showing the screen. Anyways, so to resume, like if you look at credit card transactions, right? There's actually so many ways in which you can analyze whether a credit card transaction is fraud. You can take multiple different approaches, right? So one way of doing that is, say you wanted to model the credit card transactions based on some of the data that is attached with each transaction, right? Then you could maybe look for anomalies in the data. So what is an anomaly? So when you think about it, you could think about it like this. Imagine there is one block of transactions that is legitimate, right? These would, you could imagine, form a cluster where they are kind of similar in nature, right? Or you could see that these transactions are more common, therefore they would form clusters of higher density, or they'd be clumped closer together in terms of the features they have. The anomalies are the ones that are quite different, right? So if you find some sort of anomalies, then an unsupervised, sorry, I'm going too deep, sorry, never mind. Yeah, but you could find some sort of anomalies in the data, and then those anomalies could be investigated further for fraud. So this is a sort of example where you clump data and you form little bands of groups of data. And you can kind of make interpretations, or you can make conclusions or investigations based on those separate clumps. So yeah, that's a different kind of learning algorithm. So that is basically an unsupervised learning algorithm as opposed to the housing price prediction thing, which is a supervised learning algorithm. Yeah, so moving on, yes. So supervised learning, it basically involves a sort of learning where you have the right answer, you get a bunch of data. It's basically like how you learn in school, right? You learn a bunch of stuff, you get the right answer, then you go for the testing data, and then you try to predict the testing data. And the testing data basically serves as an exam does for us in university. The unsupervised learning, like I just said, is about finding clusters of data points from large volumes of data. So just something for you guys to think about, because I want you guys to remember that this class is not just some sort of formal thing where you guys take notes. It's to get your mind sort of stimulated in different sorts of topics, okay? So one thing you can imagine is, you know how I talked about how you find some sorts of anomalies in the data? Well, the anomalies only work when, it only works when two things happen. One, the anomalies are significantly different from the other chunk, the main chunk of data. Let's take a credit card approval, for example, okay? So assume only if the credit card transactions are significantly different from the normal ones, would they be standing out as anomalies? Otherwise, they would basically clump together with the other transactions in our model of data. So these are little things you guys need to take note of when deciding which algorithm to use, for example. And the other thing is you need to look at whether your unsupervised learning algorithm, how does it separate stuff? Does it look at the density of the data, or does it look at something else? So for example, sometimes unsupervised learning algorithms, they separate the clusters based on how dense the training data points are clumped together, okay? Now, this only works if stuff is anomalous. Now imagine if all your anomalies are of one type, okay? And all your anomalies sort of clump together. Then you would not be able to detect it as some sort of low density area in your model, because all the anomalies would have clumped together. It's not an anomaly just far astray from the main dense bunch. So I don't know if you guys can sort of picture or understand what I'm talking about. There's different ways of looking at unsupervised learning algorithms. Anyways, moving on. Anyways, in this course, we're not going to really look at unsupervised learning algorithms. This is just for something that you guys can explore in your own time, what I just talked about. I'm going to share a link with you guys of like a nice talk about possible unsupervised learning algorithms that you can use on credit card approval. You guys can check it out. It's like a YouTube talk. It's not very technical in depth, but you can see basic high level view of the concepts. Anyway, so the next thing we should probably talk about, sorry, one moment. Then, yeah, the next thing we should probably talk about is training data, testing data, and validation data. I think Amadeus touched upon this last week. Did Amadeus touch upon training data and testing data last week? Yeah? Yes, Long Hao. Long Hao, can you? Long Hao, you're muted.
I don't think so.
Say insurance company's data. He didn't use the trading data.
Okay, cool. So, yeah, so we have different types of data. I mean, we get a bunch of data in supervised learning. And by the way, just to let you guys know, in this session and for most of this course, we'll be focusing on supervised learning algorithms. So having said that, we've already switched focus just to supervised learning algorithms. So just take note of that, right? So in supervised learning algorithms, we have we separate our data into training data and testing data. This testing data is also further sort of separated into something called validation data and then testing data. Okay. But if you're not doing it at a high level, you can do training data and testing data only. So this is a meme that I made. I thought I'd make the presentation more engaging. So hey ho, right? But yeah, so what validation data actually is that it is different from testing data in the sense that you are not tuning your individual model per se, okay? You're tuning something apart from your individual model. So for example, models can have different levels of complexity. And the more complex model is not necessarily the best model all the time, okay? So, but you don't really know when you see a bit of data, which sort of model do I go for, okay? So how do you decide which sort of model do you go for? You do not want to test which sort of model on the testing data, because once you test it on the testing data, right, the testing data has been tainted essentially because you are deciding on which model to use based on that. You can think of this as meaning that the testing data is seen by the model already. So that is not a good way of going about it. It's not a good way to see whether this model generalizes in all of the other things. So that is why we have something called validation data. For this sort of extra stuff, where you're, for example, ascertaining which model to pick rather than just tuning the model itself. I don't know if that computes with you guys, but I hope it does when we go to the next parts of this, lesson. Something for you guys to explore is, what validation data is, what it's used for, and that's why, I put the explore tag over there. So maybe you guys can just, read up on your own time, right? First up is linear regression. I mean, the main topic of this, the main thrust of this lesson is linear regression. And yeah, so linear regression basically, yeah, like I just talked about earlier, it's like predicting housing prices is an example where you can use linear regression to do this. Okay. So the question is, what exactly do we have to have in order to be able to predict something using linear regression? Actually, you know what? For linear regression, right? I feel like the best way for me to like kind of highlight some stuff, because most of you don't have a math background, so I think it's best to sort of illustrate this. Let me share screen on my iPad, and that will allow me to illustrate what linear regression basically the concept is. Can you guys see my iPad screen? Can someone please unmute and just let me know?
Oh, not yet.
You cannot see my iPad screen?
Yeah, we can't see it yet.
Okay. It's unfortunate. Okay. Good. Okay. Sorry. Do you guys see my iPad screen now?
No, we don't.
One moment. Do you see my screen now?
Nope.
Nope.
Not yet.
Still no.
No.
This is working just before. Okay, sorry, just one moment. Yeah, I'm trying to figure out what's happening. Okay. Sorry, guys. One moment. Sorry. Yeah. Is it sharing now?
No,
No.
it's not.
No.
The only solution I can think of is that I leave the call on my computer and I just go on my iPad instead. Okay, but I run the risk of. Okay, I'm not sure what I run the risk of then. Sorry. Okay, let me try doing something else. Okay, this is my last scope. Yes, okay, I think when I share now. Okay, I think the echo is crazy. Okay, can you guys hear me now? Yep.
Yeah.
Okay. Okay, I think now it should work. Let's start. Yeah, can you guys hear me? And can you guys see?
Yeah. Yep.
Okay, so linear regression is basically this concept of mapping a vector in n-dimensional space of, I mean, let's just take real numbers in this case, and then giving out a single value which is in obviously R. So in this case, a linear regression model would look something like, let's just say L of X, yeah? X is all the feature your model gives you. As. Yeah, so L of X is just like, let's just say AX1 plus BX2 plus CX3, that sort of thing. And then basically X1, X2, X3 is like, sorry, my iPad is lagging. That is unfortunate. Yeah, so basically it's like X1, X2, X3 is a vector, and that is converted into a constant, into a single number. Yeah, so X2, X3, and the function the linear regression function maps it into a single value. Let's just say Y pred, like a prediction. Yes. So this is basically the concept. Now, let me get back to sharing on my computer. Yeah. I hope there won't be any technical difficulties from here on in. I'm sorry for wasting like 5 minutes of your time. Yeah, let's continue. Okay. So, what exactly do we need to have in order to be able to predict? Given a new unseen input, tell us an output which we think is most likely. That's basically what any model does. And same thing with linear regression. Linear regression is not one of those probability models either, where you get a probability as an output. You just get the measure of the value. So in a more mathematical sense, we need to find a sort of function that approximates the ideal function that actually maps the relationship between these two inputs and outputs, right? Moving on. Yeah, so there's a bunch of functions we can use. And remember what I talked about validating data, right? So validation data. How do you know which of these models to use? You don't quite know. So you can try these models. After training them on the training data, you can go on the validation data and use these models on them. And then you can see which one performs best. Then you can use the testing data to see how well it generalizes. So that's why we have three sorts of segments of data at a higher level in machine learning. So does this make sense to you guys? Guys, any thoughts on this? I don't know. I want to see if you guys are following what I'm saying.
Sorry, what's heuristics?
Okay, heuristic is basically a guiding principle you use. Like, so for example, a heuristic for housing prices might be houses in a better location or like a more wealthy location cost a greater amount, or they have a greater resale price. So that is an example of a heuristic.
Oh, so you mean like when we choose the function, we use like common sense, is it?
We try to use common sense, but sometimes it's very difficult to use common sense to come up with a model. So, for example, you can imagine that this mx plus c, right, is like mx. How do I say this? It's like mx1 plus ax2 plus bx3, and it keeps going on and on. That is how do I say this? That is a more complex model, and you cannot exactly tell on the surface which one is better. So you might try each of these models and see which one is better. I know that might seem quite expensive computationally or like with time, but legitimately this is what people do on projects. They try different models on the data, and then they go from there. Yeah. So anyways, moving on. Yeah. So in terms of linear regression, we're assuming that the linear regression function would seem good here. Then we look at what are the best coefficients. So a linear regression function, right, would look something like this. Sorry, wait, let me go ahead to. Actually, you know what? No, never mind. Let me stick to the agenda. Yeah. So the first thing we need to establish when we're training our model is how do we measure the success of the model? Suggestions on how we would measure this.
Rama, you're lagging quite a bit. Hello?
Hello, can you hear me?
You are lagging a bit, so I think just fix your internet a bit. Yeah.
Yeah, can you hear me now?
Yeah, okay, it's better now.
Okay, can you guys give me an idea of what you guys would use to measure the accuracy of any prediction? What is the best thing that you can think of? And this is something that's quite common. You guys should have done this in physics or
error.
A physics A level or something like that.
The error?
Yes. Why? So what sort of error would be used to measure the accuracy?
So like the difference between what your model predicts and like the actual data.
And of course, to negate the fact that you can go over or under, you want to ensure that over and under get the same sort of level of weightage where those differences, right? So that's essentially what we do to measure success. There's no direct way to sort of measure success because success is a very difficult metric. So we go the negative way. It's always very easy to criticize, and that's kind of what we do here. So we just take the error, right? So the error that we take is the root mean square error, and that is the sum of the squares of the distances between the actual points and the prediction of the model on the graph. So just since in this case we are outputting a single value, it's not, you don't even need to take the difference between two vectors. You just need to take the difference between two values and square it. The difference between two values being the actual value and the predicted value, right? There's some debate about sort of which distance you would take to measure the error. And there's this more complicated way of doing it, which is measuring sort of like the perpendicular distance rather than the vertical distance, and then measuring that and then going from there. But that would not exactly be root mean square error. That's a different sort of error. And for the simplicity and sanity, we just take the vertical error. But just something you guys can obviously explore on your own time, the perpendicular distance and what difference that makes. So what are the advantages and what are the disadvantages of I see that I'm lagging quite a bit because I see on my iPad how slowly the slides shift. I apologize for that. I only can go as fast as the NUS Wi-Fi permits me. So, I can't do much about that. Anyways, so in this case, optimize the function to find the best coefficients. That's exactly what we do in most machine learning algorithms, right? And that is what we do here as well. So what is the advantage and what is the disadvantage of linear regression? The advantage is that it's simple and it's understandable. The disadvantage is that what if it's a function that is not good? It's either too complicated or too simple for the data. So this is something we're going to come to later, which is bias and variance, and what the issue is with bias and variance. And the other issue with linear regression is that if you have a significant number of outliers, you run into further problems. Okay, so let me just show you what I mean by that. So in linear regression, you do run into this issue of do you guys see my screen? Yes?
Yes.
The iPad? Yes, okay. So anyways, so basically the issue with linear regression is basically you have something like this, and then you have, say, a few points, say this, whatever, the x-axis, y-axis, and you have a few points like this. If you don't have many points, right, then the issue is one example that's an outlier like this will entirely skew your data. And that is something that's an issue with linear regression. Obviously, this only occurs really with when you have very small amounts of data. But often you will see that in linear regression problems, you do have a small amount of data. And this issue does pop up. So yeah, something to take note. And another type of situation where this issue crop up is like when the anomalies form. The anomalies aren't so much anomalies because they form a not insignificant part of your data set. So you can imagine if it's like 2 out of every 10 points is a bit askew, then you would run into this sort of problem. Going back to this. Okay.
Is there a general kind of minimal number of points you need to form a linear regression?
There's no golden rule about it. But what you'll understand is that it also depends on it also depends on how many features you have. So for example, if you have more features, right, then your model gets more complicated. Okay, and I'm going to come to this point about variance and bias. Okay, and I'm going to explain to you then what I'm going to be able to explain to you about the answer to your question better. So let's get to that part. Yes. So the next thing itself is bias and variance, right? So bias is basically the idea that your model is skewed a certain way. Okay. So the model is sort of for lack of a better word, biased in a certain direction or biased a certain way. essentially bias and variance differ in this. Bias is non-responsiveness to new data, and variance is too much responsiveness to new data. Okay, so these are two separate problems in that sense. The bias error usually props up when, okay, just to, let me see if I can use the whiteboard and Teams. Actually, no, never mind. I will just go with my trusted iPad. Okay, so the idea of bias and variance is if you have, let's say this sort of thing, right? Let's say that your model is like this. Okay, so let's just say f of x is just you only have, let's say, some this, right? Like where it's not even looking at the input parameters that you get. It's just giving out this constant, which is theta subscript 0. Okay. So if you just have this sort of theta subscript 0 and your data looks something like this, right? And then your theta subscript 0 would just basically be a straight flat line. So this is a model where you see there's high bias. Okay. Now, the opposite of this is, let's say there is some sort of model where you have let's say theta 0 x0 for some, so rather than this theta 0 plus theta 1 x1 plus theta 2 x2 plus I mean basically you have a more complex model, right? What will happen with the more complex model is it will be able to do all sorts of again my iPad is lagging. Okay, essentially, you will be able to construct a more complex function. A complex function, as in there will be a lot of points where the function turns, that sort of thing. Okay, so this is the sort of function that you can generate when you have more parameters. It sort of intuitively makes sense, right? If you only have this sort of one parameter that you can change as opposed to this, then your function is sort of restricted and it's not as flexible. And this is what you notice with simpler models. There is a bias in simpler models because as you get more and more new data, and the new data doesn't conform to this sort of simplistic model, because when you get new and more new data, the your function won't be able to approximate that data as well, right? So in that case, you see the issue of bias because the model doesn't really improve when the new data comes in because the model can do only this much. It cannot do more than that. It cannot bend and contort more than that. So that is a case of bias when you have too few parameters, right? And too few parameters is something that comes up when you don't have enough features because you just don't have enough features. The other thing is when you have too many features, you have this sort of contorting function, right? And let's say that your training data only gave you, let's say, 10 points, okay? There's only 10 training points. This is not very much at all, okay? But let's say the training points were in this sort of way, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then your function would go something like this. Something like this. And the issue with your function going something like this is it is too tailored to the training data set. You cannot know that the future data that you get to this model is going to be just like this. And this is the issue of variance, where your model is too responsive to changes because it's so complex that it has so many of these parameters that it can tune and move around, so many knobs that it can basically turn around, that your model is very sensitive to new data. So for example, let's just imagine that this data point went away, and let's just say that this data point was here. The very fact that this data point was here, because this is a very complex model, it can even go this way instead of this. And this would cease to exist. This is not a model that we want to see. This is not a model which is good for generalization across your new data. Because can you imagine if just one training point went away and your model shifted in this sort of manner? That would be very dangerous. And in your testing data, you would find that it would not generalize very well. So we need to strike a balance between bias and variance, right? To see which model approximates well to the training data, but also generalizes well for the testing data. Also on the subject of when you find yourself in the same case of bias, right? Say for example that your x is basically all the inputs. Just keep that in mind. So let's assume that there are only 3 input variables. So let's call them x1, x2, and x3. Okay. Now you might think that x1, x2, x3 for a very complex function, it doesn't yield you much. You might think the maximum that you can do is f of x is equal to theta 0 plus theta 1 x plus, theta 1 x1 plus theta 2 x2 plus theta 3 x3. So this you might think is the maximum that you can go. Can someone give me some suggestions on maybe how we can make this model more complex? Say that we are only given 3 input data points for each thing. So like, for example, for the HTB resale price data, let's assume that Y is the price. And let's just say X1 is location data. Let's say it's numerical for some reason. Let's say size, wealth of neighborhood. So we only have 3 features. How can we construct more features from this? Can anyone offer me some suggestions? Any ideas?
Add a polynomial term.
So can you give me an example of that polynomial term?
X1 squared.
Yes, that's good. Yes, so you can have x1 squared, you can have x1, x2, and obviously you can attach parameters to this as well. So then this would become theta 4, theta 5, and that sort of thing. Okay, so this is a way in which you can engineer more features, okay, into your data set. And yeah, so this, theta plus, right? So anyways, yeah, so this is a way you can increase the number of features and you can sort of reduce the bias. But there's only so far, there's only so much that this sort of method can do. And this sort of method is very expensive and very costly. It takes a lot of time to train a model like this. And also it's very difficult to decide which features to use. So for example, over here we have x1, x2, x3, right? So if I were to make pairs out of x1, x2, and x3, you can imagine there's already, what is it? You can think of 3C2 pairs. So basically that's 3 pairs that you can make with x1, x2, x3. Imagine if you had like 5 features and you were trying to engineer 10. That gets more complicated and so on and so forth. So I hope you guys are following in what I mean with the combination. If you have like 5 features and you need to select paired features to add on to the model, how do you decide which paired features to add on? That's a lot of trial and error. That's a lot of trying stuff and finding out that it fails. So that's a problem. So anyways, let's get back to it. I really didn't think this would go this slow. Yeah.
Can I ask a question? So the FX you drew, that's not linear regression, right?
It is linear regression. So linear regression is
the linear regression supposed to be just a straight line?
Well, linear regression is, in the simplest of terms, yes, it is a straight line, but that is only, I mean, you can only represent it as a straight line when you look at it in 3 dimensions. I think beyond that, you need to look at it in a more abstract sense. So, I mean, obviously, when you look at it from 3 dimensions, you can see sort of the line, right? Or 2 dimensions, rather, it's more easy to see the line. But when you look at it in abstract sense, what it does is basically take multiple parameters in a vector, and then it maps out to a single sort of value. Now, you know how I said that there's x1 square and x1, x2, right? I know that might seem a bit counterintuitive, like it's a polynomial, but imagine if you had a bunch of rows of data, you had x1. Imagine that you just squared all the values of x1 and then you added it to your data set. And that it was just so it's basically the same thing in that sense, right? So this is still linear regression.
Again.
So I just want to confirm what you just said is like, as long as the coefficient is linear, then it's linear regression, right? Can I understand it?
Yes, that is correct. That is correct. Okay. So again, in an abstract sense, I want you guys to remember that linear regression is about mapping a vector in Rn to a single value. That's essentially what linear regression is. And x1 square is essentially just an x4 or an x5 or whatever the nth feature that you're making. The x1 square is just another feature. So yeah, in terms of like, okay, so you know, you were asking about a line, right? So let me just show you what a line would look like. Okay, and okay, I didn't know that this would go this slow. I was actually worried that I might not have enough content to fill the time, but it turns out I do. But then that was kind of partly because of technical difficulties, but hey, or whatever. Okay, so assume that we have something like this, right? So if I have the graph x square plus, sorry, x1 square plus x2 square is equal to 1, right? Are you guys familiar with this? This is the equation of a circle, right? Right? Okay. So if I would say that this is an x2 axis and this is an x1 axis, the decision, the sort of the line you would see would not be a line, it would be a circle. Okay. And this is not what you think is linear regression. But if you just were to take this axis to be x2 squared and x1 squared, you just relabel it, which is very valid to be honest, because x1 and x2 are just features that we are putting on a graph. So, and similarly, x2 square and x1 square are features that we are putting in a graph. So if that happened, x1 square plus x2 square is equal to 1 would just be similar to like, it would be like this. It would just be a line. Do you see what I mean? Do you get what I'm trying to say? So it all depends on how you look at it. And how I look at it is mapping a bunch of features in Rn to R. So that is the concept. Anyways, yes. So yeah, I don't want to read through the slides because I think I've explained bias and variance to great length already. Okay, I don't want to labor too much over this one either, but the point is similar to what I was talking about before. You can remodel your features. You can take your feature and, for example, sign of that feature and make it a separate feature, and then you can do linear regression on including that. So that is the whole point here. So, for example, if I just were to do sign on a bunch of x values, right, and then I were to put it in a column, and say a third person just came and looked at those values. To the third person, it's not any different. You're not thinking, oh, it's a sign of this or something. You're just saying, these are a bunch of values. This is a feature, set of features. I mean, set of values for a feature. So anyways, so this is a kind of case study sort of example. So, okay, what an ETF, for example, is in the world of stocks, in the stock market, right, is basically a basket of stocks, okay? So an ETF is basically a bunch of common stocks that have, say, a common industry or something like that. For example, renewable energy. So then there'll be a renewables ETF or a solar ETF. In this case, let's just say that we are modeling the revenue of oil firms essentially, and we're taking, let's just say there are three features that we're taking. Okay, okay, so let me go to the notebook and hopefully it runs. So basically, I will share the code with you guys later, right? So basically, the whole idea is that when you run the code, you will see this is basically single variable regression that we're showing here. So we're taking each of the features and we're plotting it against the revenue. Okay. So in this case, remember that we have three features and we are plotting it against the revenue. So we're only plotting one by one against the revenue. So this is feature one against the revenue. Then we have feature two against the revenue. Then we have feature three against the revenue. So yeah, this is single variable single variable regression, right? So you can see when we do this, you get a certain root mean square error. And yeah, I'm going to come to the rest of this in a bit. Yeah, for now, we will go back to this. So let me get you guys familiar with some of the notation that we use. And this notation is for neural network regression, and not just for linear regression, it will be quite useful for a lot of things. So when you look at this, right, you see the x, you see the one on top, and you have the one at the bottom. And you see the x here, the one at the top, two at the bottom. Similarly, you see x2 at the top, two at the bottom, all this. Now, can you give me an idea of what you think the numbers at the top and the bottom, what do they represent? Intuitively, do you guys see it?
It's just the polynomial.
No, so this is basically the x value for feature one, the x value for feature one, x value for feature one, right? So the thing is, these are different training examples, okay? So these are different training examples, and you have the label for these training examples. By the way, the output, the desired output, right? Whatever this the name of the desired output is, that is called a label. Okay, so that is a terminology that you should get yourself familiar with. So the label for this data set is this, and you look at the label, it has a superscript 1 here. Okay, so the superscript superscript tells you which example it is. This is the first example, training example, second training example, third training example, fourth training example. Similarly, over here on the superscript, you have the first training example, second training example, third, and so on. Over here in the subscript, you have the number n of the feature. So in this case, it's the third feature, therefore the 3 is here. Second feature, therefore 2 is here. First feature, therefore 1 is in the subscript. So get familiar with this notation. Okay. So now, what your equation might look like is given in these examples. Okay. And this is what I mean in terms of feature engineering. You see over here, there's a square root. Okay, wait, I should probably go full presentation. Yeah, sorry. Yeah. So over here, you can. Yeah, you can see over here that this is an engineered feature. 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 But this is still linear regression. Okay? This is still linear regression. Even this is an engineered feature. So what you have over here is different model ideas, and you don't know which one to choose, right? So the way you find this out is with the root mean square error. Okay. And this is where, obviously, like I said before, the validation data comes in. Do you guys kind of follow the intuitive, the notation? Does the notation make sense to you? Are you guys very confused by the notation at this moment? Anyone?
So the I, as you say,
Yeah?
is you said training example, right? Is that the same as training set?
Training example is basically any example from the training set. The training set comprises of multiple examples. And this is just an example from the training set.
It's just a single data point.
Yes, correct.
Okay, thank you.
So for the future, right, we won't be referring to our prediction as y. We will be referring to the actual value as y, and we'll be referring to our predicted value as something else, okay? Which I'm going to show you after this. But you guys do get the idea of manufacturing these features, right? Does this compute with you guys? Do you guys see what I'm trying to do? I mean, do you follow? Does it, or is it still feeling a bit? Just let me know and just stop me if you guys have any sort of trepidation about this. Yeah. So yeah, I'll continue. Sorry. Yeah, just give me a moment. Let me just drink some water. Okay. So, like I said, we're not going to be referring to our y as the same thing as our prediction anymore. In this previous slide, we were referring to it as our prediction. This is our prediction, by the way. You can see clearly that this is something that we have constructed, right? These theta values are something that we have learned from in our model, and these are things that we've applied to this model, and this is the prediction. But now we're going to refer to the prediction in a different way. We're going to refer to it as a function h subscript theta of xi. Okay, and remember that xi comprises of xi1, comprises of xi2, xi3. So this xi, it comprises of all of these. You can think of xi as a vector comprising of xi subscript 1, subscript 2, and subscript 3. So this is a function of that vector. And Brinal, can you just shout out to me what what is this xi exactly?
Wait, sorry. This is the
This is the prediction function that we have. This is the input to the prediction function.
Yeah,
so
yeah,
what is the input to this prediction function? Sorry. Okay, so this again is the vector which comprises all of your input features. Let's say x1, x2, and x3. X subscript 1, subscript 2, subscript 3 are all your input features, and x is the vector that comprises each of these. The superscript I, just to refresh your memory, is the fact that this is for one single example. Okay, This is for one single example. Okay. In the training set, you will have multiple examples. That is why we have given the value I. I can take on any number of examples from 1 to the number of examples n in the training set. Okay. Now, the error term for each prediction for a certain value of theta. So remember, we talked about there being an error when you predict, right? And this is how we formally denote it in machine learning notation. So the reason why I'm running through this notation here is not because I want to confuse you guys or make it seem like, this is a harder thing than it actually is. The reason I do it is because when you guys read more complex papers about neural networks and stuff like that, for those of you who have not done that, right, you will see that a lot of the language they use is similar to this, right? And when you see that, I don't want you guys to feel intimidated at that moment. So it's better you guys get exposed to this at a simpler concept and at a lower level, a simpler level. But yeah, many people, they love to make something look more complex than it is to make them seem more, how do I say this, more skilled than they are. And I'm not trying to do that here. So in this case, you have the sigma and you have the superscript I is equal to the actual value y superscript I minus the h theta x superscript I. So to make you guys sort of understand why we call it h subscript theta, h basically stands for hypothesis. Okay? Hypothesis from your science days, from your physics, chemistry days, is basically some sort of statement which you are trying to prove, right? And similar to that, over here, this is a function whose accuracy we are trying to prove. So that is why we call it h subscript theta. So this is something that's common in the machine learning world as well. The reason why there's a subscript theta is because the function involves infusing the inputs with theta values, basically with a theta vector. This theta is basically a vector containing the theta 0, theta 1, theta 2, theta 3. Now, for when you're modeling something, right, you need to have something like which is a cost function. A cost function in machine learning, in specific terms, linear regression and neural networks, or even in logistic regression, which we'll cover next week, is basically an error function, measures the error in the model. In this case, we are taking the root mean squared error. So if you look at the cost function, we are calling it j of theta. And you can even, I think nowadays people started calling it L of theta, if I'm not wrong. But yeah, j of theta is also acceptable. You can call it whatever you want, but in terms of what is commonly used in the machine learning world, right? So now we have a summation from 1 to n of y superscript I minus h theta x superscript I the whole square. Does anyone sort of have an idea of what this function is? Can someone verbally in layman's terms explain to me what this function is saying?
It's a measure of how bad the function is at predicting the data.
So why do I have a summation 1 to n here?
To sum over the training data from the first training data to the last.
Yes, thank you. Yes. So yes, that's correct. Now, yeah. So the reason why, so the I 1 to n is because we want to sum it over all of the examples within the training data. Remember, we are squaring it because we want to represent the positive error and the negative error with the same weightage. We don't want to, cancel them out or anything like that. So anyways, now the cost function, we can, okay, so we're trying to optimize for the cost function, right? So from your days in high school, from your days in university, year 1, year 2, or yeah, whatever, right? You guys know that optimizing any function, any optimization problem, what is the first thing that springs to mind? Can someone give me the first thing that springs to mind in an optimization problem? What is the concept we use in mathematics?
Sorry? Least square or something? I'm not really sure.
Differentiation.
Least square?
Yes. This is a differentiation.
Gradient equals 0?
Yes, correct. That is the first thing that we think of. Gradient equals 0. So now if I have a gradient of a function, and I'm trying to find the gradient equals 0, right? Or I'm trying to find the lowest point, sorry, the point where the gradient of the function is equal to 0. If I were to divide that by a constant, divide the function by a constant, would the location of my gradient change? Would the location of the point where the gradient equals 0, would that change if I were to divide the function by a constant?
No.
No, right? I think that was sorry? Is someone not convinced by this? Is someone not convinced by this sort of idea? So like if I were to if okay, you know what, I will again move to just visualizing this so that actually, you know what, the best way to visualize this is not on my iPad, it's on GeoGebra. So GeoGebra, sorry, the graphing calculator, okay, please don't lag. Sorry. Again, it's very difficult for me to show these things. Okay, so you have this AX, right? And sorry, no, rather than this, we should do something different. So AX square. We'll just see. What's this? No. Okay, you know what? Never mind. Just sorry. Yes. Okay. Now, this is not the most rigorous mathematical proof you'll ever see in your life, but sorry, it's so annoying, but I just wanted to show you the intuition. Sorry, did not break this with a question. So. Yeah, so you guys see this, right? So over here, you see that the A is on the outside. And now you see that the point where the gradient is 0 is this, right? Now imagine if I were to toggle this. So you know, the, okay, sorry, yeah. So okay, again, if I were to just keep the same sort of, yeah, okay. So if I were to toggle this, right? Do you see that the x value of the minimum, does not move left or right? You see that the minimum value itself will change, but the point at which the minimum value is achieved will stay the same, right? And that is exactly what we want. We don't care what the actual value of this is. We just want to find the point where this is minimum. So this could be millions for all I care. I just want to see that this is the minimum. So how we scale it doesn't matter, right? This is not the most rigorous mathematical proof you'll ever see. For that, you should take MA2108, real analysis. Yes. Yeah. So, anyways, yeah, that's something you can probably look into. But anyways, so I think I hope this is intuitively apparent to you guys. So, anyways, let me. Okay, I don't know why I stopped sharing screen there. Yes. Okay. Okay. So, do you guys see what I mean? Can someone just kind of affirm to me that they got what I was trying to say? Why this 1/2n doesn't change anything? So we can call the cost function this is. Right? Now moving on. So we now know the cost function is like this. And now if you look at this 1/2n, right? Let me just, I think you guys should get it intuitively. Why do we do 1/2n? Okay, I'll explain the first part. Why do we do 1/n? 1/n is because we want to kind of average the error out for all of these training examples. The other reason why we do the 1/n is because if you have a large number of training examples, n, right, this thing could go into like a very, very, very large number. And then doing computations on that is very, how do I say this? It's very irritating, yes? So we don't want that. We don't want to have too much excess storage. We don't want to do all of that excess computation. So we do the 1/n to minimum, to sort of reduce it back down to the average error, if you will. right? Do you understand that? The 1 by n part. Now, for the 1 by 2 part, it is just to make sure that the calculus that follows this is easier. Remember that when you take the gradient of any squared function, the 2 comes down. I mean, the 2 comes as a scalar multiple. And when the 2 is multiplied, you want the 1 by 2 to cancel it out to make it easier. So that is why we have 1 by 2n, and that's why we do that to the cost function. So now the goal to minimize the cost function, it can be achieved using calculus. And the goal is achieved by doing this. So you remember how, okay, I need to go back to sharing screen on the iPad. So, okay. Okay. So you remember how I was talking about, earlier I was talking about, H theta. Remember now we're calling it H theta. We're not taking Y as our prediction anymore. So then I was saying H theta of X, X I is equal to theta of theta 0 plus theta 1 of X 1 plus theta 2 X I plus so on and so forth, right? Now the whole principle is that when you have the cost function that looks like this, that is J of theta is equal to 1 by 2n I is equal to 1, 2n yi minus h theta xi the whole square, right? So this is the cost function, right? And this is your h theta above here. So this is your h theta, and this is the cost function. I've been lagging again. Not my day. Sorry. Can someone maybe give me an idea if they're feeling lost or something? Can you guys just PM me on the chat? Or like PM me even on Tele or something? I won't. Don't worry. Like when I share screen, I'll make sure that it's not visible or whatever. So yeah, just let me know if you guys are feeling completely lost about something. If you guys are feeling completely lost, then maybe try to be more specific about what you're feeling completely lost about. So anyways, I think my iPad is back on track now. So basically, you are how you optimize this is you optimize each theta j value. So the theta j value, the theta j values. So theta is equal to, it's basically a vector of theta 0, theta 1, theta 2, and then dot dot dot, right? That's basically the vector. So you can generalize this as theta j. Okay. So how you would optimize each theta j, how you would optimize each of these theta j's would be this way. Okay. So this is the formula to optimize the theta j. Theta j is equal to theta j minus alpha into the partial derivative of j of theta. So let me first explain what the alpha is over here. The alpha is an arbitrary constant. Okay. It is your choice, entirely your choice. It is what is called the learning rate. Okay. So how quickly does your model learn? That is what the learning rate is. The recommended value for the learning rate is somewhere around 0.1 to like 3. Anywhere in between this range is fine. You run into problems when your learning rate is too large, and you run into problems when your learning rate is too small as well. Problem. I will show you why it is a problem in a bit. Okay, so this is what we do. Now let's try to go into that. Okay, so theta j is equal to theta j minus alpha into this derivative, right? So now how do we do? So we can just expand that out. We can say alpha, and just remember what the j of theta is. Remember we wrote j of theta what it is. So I can just do the partial derivative of 1 by 2n I is equal to 1 Oh, yeah. Okay. I might be mistaken, but from what I've read, yeah, you use something like 0.1. And actually, sorry, I don't think you would say 3, so 3, something like that. That's from what I know. Maybe I might be wrong. If I'm wrong, then maybe you guys can just look it up, send me the link or the article, and yeah, just share on the group, on the Teams channel. Anyways, so h theta of xi square. Yeah. So that's have I gotten all the brackets right? I hope I've gotten all the brackets right. I don't think I've gotten all the brackets right. No, that's right. Sorry. Okay. Sorry. Yeah. Have I? Yes, I have gotten the brackets right. So this is basically what we're trying to do. Just keep in mind that alpha is always positive. It just makes intuitive sense that your learning rate of if anything is called a learning rate, it should be positive. So just keep that intuition in mind. So now what we have to do is we need to do this. We need to do this simultaneously for all the values of j. So that is how many ever parameters that we have here, how many ever parameters that we have in 0, 1, 2, to whatever n number that we have, we need to do this simultaneously. So what does that mean simultaneously? That means that whenever we're calculating this, so for example, first we do this for theta 0, right? Now, once we change the theta 0 and we try to, once we change theta 0, right? This means that theta 0 is changed to a new value. Now, theta 0, once this function is applied, becomes a new value. Now, when we do the same process for theta 1, we cannot use the new value of theta 0. We need to use the old value only, right? We need to do this all the way until theta n. And once we get to theta n, then we can move on to the next round of the cycle where we use the new theta values in the function. Because remember that the theta values are in this function. Okay. So now going back to my yeah, Jotham, I saw your message on the channel, right? So just text the link over there or whatever, and sure, that's not an issue. I'm happy to be proven wrong. So so now this is what we do. This is what I just showed you on my iPad. So you basically do this for each of the theta values and you do it simultaneously. Now, when you do this, when you use calculus, you use the partial derivative, right? And partial derivative essentially means that you keep theta j constant in, sorry, you keep everything except for your theta j constant. So for example, when we were doing, if we were to do this as theta 0 is equal to theta 0 minus alpha into partial derivative with respect to theta 0, we treat every other theta subscript as a constant. We only treat theta j as a variable, and then we take the derivative. Okay? If you were to look at this, right, I keep making the mistake of toggling back and forth, but that is unfortunately what I just have to do. I hope you guys will follow the calculus. So I don't want you guys to get intimidated by the partials. So for those of you who are into math, partials are just really simple. So just keep in mind that this is what we're doing, right? So we are trying to do, so let me just list it out. So this is basically y I minus minus theta 0 plus theta 1 x1 plus theta 2 x2. Let's just keep it to this. Let's not go further than this. Okay, it can be theta 3 x3 and so on and so forth, but let's just keep it to this. So what a partial derivative just means is that you are keeping, so if you have this, and let's just say so this is, we're calculating it for theta 0 equal to theta 0 minus alpha into, and this j would be 0 in this case. So in this case, we treat everything except for the theta 0 as a constant in this function. Okay. And when you do that, essentially you come to the result that you come to the result where you come to the result where basically theta j. Again, my iPad is lagging. Okay, yes. Theta j is equal to theta j minus alpha to 1. Because if you keep in mind, right, keep in mind where this extra ij comes from. So first of all, keep in mind this is the case, right? So when you do this, the whole thing squared, right? The 2 comes down. Remember, when you do a derivative, the 2 comes down. So you basically the 2 comes down and cancels out the 1 by 2n. So 1 by 2n into 2, the 2 and 2 cancel out. That is why it is just 1 by n. Now the reason why you have, so now the 2 is gone, therefore the power here is 1, right? So remember that h theta I is basically this. This entire thing is h theta I. So this is just the same thing and it stays, right? The 2 comes down and the 2 comes down and therefore the 2 is no more and it becomes a 1, right? So where does the thing xij come from? So the xij comes from the fact that in the case of the theta j in the h of theta will be theta j xj, right? I told you to treat everything except for theta j as a constant, but this as a variable. Now, if you were to do a differentiation with respect to this, xj theta j, this is to the power of 1. Now, this would basically just come down, and the derivative of this would just be xj. Now, we're doing this for particular examples, so therefore it is xij. That is why you have the xij term here, right? I hope that sort of makes sense. You guys can look at the math over on the slides once we come back to this. Okay, so let me just read again. Okay, so the other thing to take note, right, is this theta. You know how I talked about theta j, right? Now, if it was theta 0, so everything theta 1 as x1, theta 2 as x2. But what is theta 0? Theta 0 is just a constant term, right, in that function. Theta 0 is just a special case where the xij value would basically be 1. Because remember, in our function was hypothesis is equal to theta 0 plus theta 1 x1 plus theta 2 x2, so on and so forth. Theta 0 next to it, the coefficient is just 1. So you can treat the xij, the j xi0 value as 1. You can think of it as just 1. So yeah, so this is just the iterative process of finding the optimal values of theta. So how do we know when to stop, essentially, right? So the when do we stop this sort of process of just doing partial derivatives and subtracting over and over? And the whole idea is given by gradient descent. So the whole idea is that you're going down a mountain, and then once you get to the bottom of the mountain, like a valley, and you get down to the valley of it, that's where you know you've reached the lowest point that you can go in your error function. So how do you find that out is that if you notice in any derivative function, right, when you're converging to a minimum in the function, let's say it's a bowl-shaped function and you're converging to the minimum, the speed at which you get to the minimum, it slows down as you get closer to the minimum. So when you look at that concept, right, it slows down. So what does that mean? So each time you do these changes, right, if the cost function, the change in the cost function is becoming slower and slower and slower, you know you're converging to that minimum. And when the cost function is not changing, you can stop and say that's enough. Or you can set a sort of threshold where you say if the cost function change is lesser than this value, that's where we stop and we say we're done. We've reached a good enough point where we can quit. So now just coming back to what the point about alpha was, right? So the issue with alpha being too small or too large is this. If it's too small, right, then so what is alpha? Alpha is essentially a coefficient that multiplies this with this and is subtracted from this. So if you want to go down to the valley, essentially, right, to the lowest point, if your alpha is slow, the changes to theta j, because this theta j into minus alpha into something. So if this is small, that something becomes small as well. So the changes that you make at each step will be smaller, and that is too small. If you have the alpha value that is just right, then you're kind of going at the right pace. If you have the alpha value too large, right, you will keep rebounding like this, and that's problematic, and that's just not good at all. So therefore, you need to have a nice, proper alpha value. So how does gradient descent actually look visually? We can actually only visualize gradient descent in 2 or 3 dimensions. So I mentioned this, right? That's why I told you when you're looking at linear regression and stuff, always think of it as mapping a vector in Rn space to just a single value or a number. So we can picture gradient descent like this. This is what is called a convex function, and you can get to this bottom point, which is also over here. You only have one minima, which is the global minima is the only minima. Okay. In these sorts of functions, you have local minima as well. So local minima aren't the absolute lowest point, but they're sort of valleys in which you can get stuck when you're doing gradient descent. So I'm going to show you sort of an illustration of what I mean. So the illustration is here. Let me show you the animation. So slideshow. So do you guys see this? And do you guys see what I mean by local minima and global minima? Now imagine your function has something like this. This is a local minima. It is not the deepest point. This is the deepest point. But once you get into this point, you cannot get out of it. That is the issue. Okay. But in some cases, the local minima is still okay. So it depends on how sort of to what level you want to do your project also. Okay. It depends on that as well. So there are 2 factors which influence where the ball heads, essentially. Can you guys think of what are the 2 factors? Or there are 2 main factors, rather. Can you guys suggest what are 2 main factors which indicate where the ball will head, this way or this way?
The starting position.
Yes. And?
Initial direction.
Yes, in some respects, yes. So the starting position in initial direction is sort of in the similar vein, right? So basically it is more about location. The second part is speed, okay? And speed is the second thing. So first of all, in terms of location, it kind of makes sense. For example, if you were here and you were rolling down here, you would get here first. You would not even see this place, right? As opposed to say you were rolling down here, you would get stuck here most likely. And that is something to take note, basically. And there are 2 factors that influence this, and those 2 factors are the learning and the starting values of the parameters. The learning rate is effectively a representation of your speed when you're going down that hill. The starting value of the parameters is what exactly 2 of you just mentioned. The direction and the starting point. But just keep in mind that the direction, right? The direction is not something you choose. The direction is decided by the algorithm, right? The direction in which you go is really decided by the algorithm, because these. So if you were in 2-dimensional space, right? So assume that the z-axis is the cost function value, and the theta values are given by the x and the y-axis. Which direction of x and y you go is determined by what result is returned to you by the partial derivative. But what you can control is the starting point, right? The starting point is something that definitely you can control, as opposed to the direction. So I stand corrected. The thing that influences it is the starting point more than the direction. Anyways, so yeah, learning rate and the values of parameters. Learning rate is something we've already discussed. Starting values of parameters is something you guys can explore. So what is the best way to start your gradient descent in a way that you reach the global minima rather than the local minima? So it's something you can do. And by the way, if you guys know something that you guys would like to share with the class, please do so. Like, for example, I know Jotham just shared on the group, right? The learning rate thing. I know that Jotham's done work in machine learning before. So for example, Jotham, if you want to come in and you want to say something, please, by all means, go ahead. You're welcome to. We actually like to see you guys share your knowledge with each other. So the analogy of gradient descent, you know what? I don't want to waste too much time with this. I wanted to keep the class to 1.5 hours, but I don't know if I can. But let's see how. Basically, you get the point though, right? Gradient descent is basically just going down a hill or mountain and then reaching basically a valley. That is the point. Obviously, you can only visualize it in 2 and 3 dimensions. 4 dimensions, obviously, you cannot really visualize it, but the calculus still stands. The calculus obviously is generalizable. Now, there's gradient descent can take on multiple types. There's batch gradient descent, stochastic gradient descent, mini batch gradient descent. Stochastic gradient descent is where you just take one example. Like, you know how I talked about a training set and you have multiple training examples? Stochastic gradient descent is where you randomly pick one of those examples and then you adapt your parameters. Then you randomly pick another example and you adapt your parameters. That is opposed to what we were doing just now, which was taking all your examples, adapting the parameters, then taking all your examples again with those new parameters, then adapting those parameters. This is just taking one, adapting, and this one is always randomly chosen. And the whole idea is that if you choose it randomly multiple times, right, at a certain point, you've basically taken all of them. That is basically the idea. It's not very statistically rigorous, but you can think of it that way. You can look into it as well. Mini batch gradient descent is somewhere between stochastic and what we were just talking about now. So mini batch is basically, you can imagine taking smaller groups and doing it. There is some merit to the idea that, there is this idea that if you use stochastic gradient descent, it's much less likely that you get stuck in those local minima. It's more likely you end up in the global minima. So you guys can look into this on your own time. So let me just say that again, stochastic gradient descent and even mini batch gradient descent, the benefit is that it's less likely you get stuck in the local minima, as opposed to a full-blown gradient descent where you take every training example for every step of the gradient descent. Now, there are other ways to find, to optimize your parameters, because this sort of calculus and adapting the theta is quite a computationally expensive one and takes time. The other way to do it is this thing, which is the normal equation. Okay, so this is something you guys can look up in your own time. So the normal equation, this X is basically all your input parameters in matrix form. The T is the transpose of that matrix. So you multiply the transpose of that input matrix with itself, take the inverse and multiply it with the transpose and then the output. So this is a normal equation function, which I don't want to get into in this class because in this class, again, I just want to give you guys the heads up that this class is not supposed to teach you everything. This class is supposed to get your, the juices flowing in your brain and for you guys to look this stuff up on your own. So in terms of these three, right, I think the minimum you guys should be doing is looking this up and seeing what it is and why the math works, for example. So as I mentioned earlier, keep in mind your starting point, your learning rate. Okay, feature normalization will come to at the end. So what is normalization? So normalization is basically scaling your features down. So you'll see that your features can take on a wide range of values, right? So for example, imagine that there's something that only ranges from between, let's say, 0 and 1. And then there's something that ranges from 20,000 to 50,000, like some income metric, right? Now you look at this and you were to compute your error or something like that. It wouldn't be fair and it wouldn't be sort of level. And that is why you sort of normalize the data to bring about some sort of balance to things. And when you bring about that balance, the other thing is you also help make gradient descent much quicker. Because, and maybe you can look this up. It's something that you should be looking up. Why does normalization make gradient descent faster? So this is sort of your homework question. You can think of it. I hate using the word homework, but it's just something you guys should take note of. Next week, when you come back and Amadeus is through time series, I want you guys to explain to Amadeus. I'll ask Amadeus to ask each of you, not each of you, but I'll ask the group why normalization helps in making gradient descent quicker. So I want you guys to just look into this. These are some links for you guys to look into why we normalize data. This Analytics Vidya article, in fact, is quite comprehensive. It encompasses most of what we talk about in this lesson. Regularization. So, okay, now this is the last part where I think I switched to my. Okay, it's not the last part that I switched to my. How much time do I have? Okay. I'm sorry if I've overrun my time a bit today because it's my first lesson with you guys, and and also with the technical difficulties, it gets a bit tough, right? So please load faster. So okay, while we're waiting, right? Let me just give you the intuition is that when you have when you have this sort of hypothesis function. Let's say that we had a theta 100 x 100. Now this, when you look at it, right, is a very complex function because there's 100 parameters. There's 100 knobs you can turn on and off, around, and adapt the model. Now, what was the issue when I talked about earlier? When you have a model that's too complex, what is the issue that you run into? Can someone remember?
Variance, something like that.
Yes, correct. So variance is the lack of reproducibility in your training data, right? And how do you, so in your testing data, the model doesn't generalize to your testing data. So the one way you can sort of adapt this in a way is something called regularization. And regularization effectively reduces the impact of these weights, of the weights. So therefore, the model isn't so tailored to the training data and it fits better with the testing data. So, so how this is achieved, right, is in your cost function, you have, okay, let's just say j theta new, and you have j theta old. And you basically add, let's just say j is equal to 1 through 100, theta j, okay? Or theta j square, or let's just say theta j square, something like this, okay? So the reason why you add this term is this would make the theta values, the weights, reduce. Because when you do a theta j square, this is a positive value, and you are adding it onto your cost function. So if you were to minimize the cost function, the theta values would be lower than they were before when you think about it. Because lowering it makes this term, this entire term, go to zero. I mean, towards zero, goes towards zero, yes. So if you were to lower the theta j values, that is reduce the weights impact, you would be going to zero then. And that's why the theta j values will be lower if you were to add this term onto your cost function. And this is something that you do to make sure that your model is more generalizable and isn't too tailored to your training data. So this is something you guys can also look into. It's a concept that is used in machine learning called regularization. Sorry, the other thing is you can also attach a lambda, like a constant to this, to adapt how much you want to reduce the theta j. So lambda can be reduced. Lambda can be adapted to reduce or increase the theta. To adapt how much you want to reduce the theta values. Say if lambda was large, if lambda is large, you j of theta large, and you're incentivized to reduce theta values more. So it's just you should look into in depth in your own time. Now we are heading to the final part of this, and the final part of this, I promise, is going to be less math heavy. You guys, this will be more just sort of a concept sort of thing. Yeah. So we're done with linear regression for now. So you guys can just see this. So we're just going to touch on this model, the KNN model. Okay. So K-nearest neighbors is probably one of the simplest models you'll ever find in machine learning. Okay. And K-nearest neighbors runs on this principle. So the whole principle is this. There is actually no learning done by this model. This model will just take your data points. So assume that there are two classes of data. Okay, there is the plus class and there's the minus class. You have training data that is put on your graph.
Currently, you're not sharing.
Sorry?
Anything. You're not sharing anything.
My okay, good. Sorry. Yes. Okay, so yeah, so yeah, you see here that basically you have the plus class and you have the minus class, and what KNN does is it doesn't actually learn anything. It just sort of memorizes your training data. So you get these data points. This is very simplistic because it's a simple two-dimensional graph. But of course, you can imagine this in an RN space where you cannot visualize it as well. So you basically plot your values, and then you get a new point, whatever the testing data point is, or whatever you want to predict comes in. You look at the number of the nearest neighbors to this point in this space, and depending on how many of the nearest points you want to take into account, you can predict the value or predict the class of this object. So, sorry, this training data. This testing data point. So, for example, if I were to only take the nearest data point, that would be this. So the nearest data point is green. Therefore, I will class this as a green object or a green data. I will give this data the label of green. Now, if I were to take the three nearest neighbors, I would still only take this, this, and this. And the majority class in these three is the green because it's 2 out of the 3. So therefore, I will class this as green. As opposed to now, if I were to go out to 7, if I were to take the 7 nearest neighbors, I will see 4 red and 3 green. So I will class it as red. So that is what the KNN model is. And you can see in this KNN model, it's not much of learning or parameters so much. It is just getting your training data and seeing what is more similar to it. So there's not much learning at all. It's quite simple, right? I think this model is much simpler than anything I've discussed so far. Is that fair?
Sorry, what's the difference between the red and the green data points?
Sorry, the red and the green are basically 2 different labels. So assume that you get data and it conforms to either the red class or the green class. So let's just say that, okay, so let's say that, okay, instead of y, right, imagine this to be some x2 and this is some x1. Imagine that each of these has some numerical parameters, okay? So let's say that x1 is income and x2 is age, okay? So we are plotting it on this graph, income and age, okay? Now imagine that the output or the label of each of these is, let's just say happy or sad, okay? Let's just say happy is the green stuff and sad is the red stuff. So we have data point, each data point looks like this. We have the income, we have the age, and we have happy or sad.
Oh.
So we will plot income here, we will plot we will plot the age here, and we will mark the point on this graph. The sign that we give to the point on the graph depends on whether he's happy or he's sad. If he's happy, we will give him a green, and if he's sad, we will give him a red. So there are 2 labels here, 2 classes here, essentially. So how do we decide when we get this sort of new data point? How do we decide whether it conforms to happy or sad? We know the input parameters of this. We know the income and the age, and now we need to predict whether he's happy or sad.
Oh, okay.
Do you see it or no? If not, I will try to go more.
Yeah, I see it.
Okay.
Yeah, thank you.
Please, sorry? Sorry, Hans?
So this one this model can be used to predict, right? It's not just to record stuff, right? The blue one is the one that I need to predict.
This model can be used to predict, yes.
Okay.
Any model is for prediction, yes. So the whole point of this is you are memorizing the data here, essentially. Now, when a new thing comes in, you just measure the distance to this. You measure the closest points to this point. to this new point that you're getting and you're trying to classify, you see what are the closest points. And then based on the majority class, you assign that class to this new point. In this case, the 3 nearest neighbors, the majority of them are green. And if you're doing this if you're only looking at the 3 nearest neighbors, you would class this as green. If you're looking at the 7 nearest neighbors, you would class this as red. So it depends on how many nearest neighbors you're looking for. That is why K is in the name, because K can vary how many of these you want to take into account, how many of the surrounding points.
Okay.
Now, this is just in R2 space. This is just in 2-dimensional space. So in 2-dimensional space, the distance to this point, right, is measured by the distance in the x-axis, the whole square, plus the distance in the y-axis, the whole square, and the square root of that. That is what this distance is, correct? The distance between this point and this point, because you need to measure the closest points to this point.
Yeah.
Right? So how would you measure the distance to this point? You will look at this line and try to measure the distance, right? So how would you measure the distance of this line? It would be by the Pythagoras theorem, right? So you would look at the x-axis, the whole square, plus the y-axis, the whole square, and square root that. That is the difference here, right? So so you just basically find the distances to each of these points and see which ones are the closest, and you go based on that. You can adapt K as you'd like. How many of the nearest neighbors do you want to take into account? So some things that you can think about is where KNN might fall short. Okay, so let me just give you an example off the top of my head about where KNN might fall short. Okay, let's say that you have some sort of image data, right? So you have my face, and then you have my face with a bunch of different filters on it. Each of those pictures with the filter on it, if it was modeled on a graph, it would be the same distance away from my original picture. It will be different in different ways, but the distance on the graph will be the same. So for example, you would run into a problem let me just give you a hypothetical example. Imagine that this is some sort of image data. I'm talking very much in like abstract terms here, okay? So imagine this is some sort of image data, and imagine that there's an image with me with a sunglass filter on it. That might be this point here. Imagine that there's an image of me with, let's say, a dog ears filter over here, okay? So that is, if you look at the distance to this point, right, of this and this, the distances are quite similar, although the images are quite different. So when you look at image data, right, using KNN might not be the best way to go about classifying images, because what KNN does is it doesn't look at the individual differences in your parameters, sorry, in your inputs. It clumps all the individual differences in the inputs into one distance, and it looks at that distance and it sees whether you're similar or not. I hope this sort of makes intuitive sense. I will run through this again during the neural networks lecture. I just thought this would be nice for you guys to explore at the start. So one thing you can look at is where might KNN fall short, and what do KNN decision boundaries look like with different values of K. So let me just show you what they look like. You guys can read about it in depth. So KNN decision boundaries look something like this. So you have a green class, you have a red class, and you have a blue class. The decision boundary means if a testing data point fell in any of these areas, which class would it be described as? If it were to go into, if a testing data point was mapped to this, then it would be blue. If a testing data point falls in this region, it would be green. And if a testing data point was mapped to this area somewhere here, then it would be red. You can look at how the different values of K, that is how many nearest neighbors you consider, how that affects the decision boundaries that are there. The idea is that if you have a smaller value of K, the decision boundary will be much more jagged. And if you have a larger value of K, the decision boundary will be much smoother. There is an optimal value of K that you need to find for your particular use case. A lot of study has been done on what is the optimal value of K. But yeah, you guys can look into how decision boundaries are affected by the value of K. So I think with that, I've come to basically everything that I want to talk about during this session. The KNN was just something to get you guys to think about stuff. So anyways, I hope you guys will look into it. Anyways, finally to summarize, basically we covered intro to machine learning. There was supervised and unsupervised learning, but I just described what unsupervised learning was for the most part. I talked about linear regression. I even made a mention of KNN. We talked about the optimization of models, which is specifically the gradient descent algorithm, which is the most important thing. We talked about normalization as well. And we're done for today. Today was just a theoretical discussion about the fundamentals of regression. Classification, we just touched on with KNN. To really get into like stock price predictions and all that, right? You should read more about neural networks. Remember what I said about linear regression at the start? It's essentially, when you think about it, it's like a baby neural network. It's a neural network with just one layer. Of course, I haven't told you about what layers are in neural networks yet, but if you looked it up, you would see that basically linear regression is like a neural network with one layer, at least at the lowest level. So neural networks build on the concepts discussed in this, and yeah, so they result typically in more accurate models. And yeah, that's basically all I have for today. You guys don't have to look up neural networks, but you know the stuff I talked about where I said explore KNN, explore normalization, regularization, that sort of thing. Please do that. For the neural networks, we will see you guys in, I think, 3 weeks. I think in 3 weeks, we'll be doing neural networks. Next week, we'll be doing time series, and for that, Amadeus will take over. For now, that's all. And if you guys have any questions, you guys can stick around. Otherwise, see you guys.
Hey, thanks a lot. Thanks a lot. Thanks a lot for the class. Thank you.
Thank you.
Thank you.
Thank you.
So the next session will be on Tuesday, right?
The next session will be on Tuesday.
Okay, thanks.
Anyone who has
Yeah,
problems,
see you next week.
tell them.
Are you going to release the slides or
Yeah, we'll release the slides.
for everyone in the CCA?
Yeah.
Okay.
See you guys.
Thanks for the presentation, Rama. Bye-bye.
Yeah, see you. Brian, are you still there? I assume you're not. Ouch. Anyways, yeah, see you. I will just stop the recording.